Okay, so let's get started. So there was a comment in the chat about is this week we start using Arena, and this week, of course, you can read ahead to Arena, but we'll start. We are going to introduce agent-based modeling with NetLogo, and then the next week will be the week that we start using Arena. So homework B1 solution should now be available online. There's another ICA activity available. Again, just a reminder, I think there are only 12 of these ICA activities and you get to drop like 7 or something like that. So they come up pretty frequently, but they're not meant to be like a major demand. Because you can drop so many of them, you can skip quite a few of them. But they are available if you do want that practice or those, the touch base on more of a weekly basis, they're there to take that opportunity, but they're not meant to overload you guys. And so, but I just remind you of them that there's another one that is available. Homework C2 is available. Some people have already turned it in. It's another 2 questions. It's related to random number generation. So that's in chapter 7. So we'll be talking about that starting next week. I'm about to release the next homework to make it available. Got it all down on paper. I just need to type it back up. And so that will be available soon. Yeah, so, and I think the rest of it we can get to a different time. Just more reminders. Again, the Rockwell Arena competition. If you are interested in using this for your final project, the entry for this is at the end of the month, September. Likewise, if you are alternatively interested in trying out FlexSim instead of Arena and using a healthcare application, then this one's entry, I think, is much sooner than that. It's like September 20th. So it's within a week. So look into that. And I don't know as much about the Simio competition, but they also have an annual competition that you can look into. So these are all kind of options that you could do for your final project, or you just do the conventional final project where you pick a local system and you do a simulation of that. Not necessarily local, but that it doesn't have to be at all tied to the simulation stuff. You should be thinking about who's going to be in your team, but you're not going to need to form teams formally, I think, until the week after fall break. So that's kind of the timeline there. And then from that point on, we'll start seeing the deliverables related to the fall project. So any questions about, oh yeah, the other thing that I posted an announcement for is that for historical reasons, the week before fall break, we have stage 1 of the exam on a Tuesday of stage 1. And then Thursday, we just have a post midterm lecture. And then stage 2 of the exam doesn't come until the Thursday after fall break. So there again, historical reasons for why that is. And I used to like to put a weekend in between stages. So people got time to think about their stage 1 before they took their stage 2. But I can also understand for scheduling purposes how some of you might want to just get everything out of the way before fall break. So you've kind of got that fall break week to kind of have more scheduling flexibility in case anyone's doing any traveling or anything like that. So I have a survey online. I won't tell you the results so far, but I'll tell you the magnitude. So there's 9 people in one camp and 5 people in another camp as of this morning, but I won't tell you which camp is which. There are 2 options. Well, option 1 is to keep things as they are, where stage 1 is the Tuesday before fall break, and stage 2, which is the collaborative version that is untimed, but you get a whole day to work with people and with your notes to do the exact same test as you did in stage 1. That's currently timed for the Thursday after fall break. So fall break is a Monday and Tuesday. There is no formal lab that week, but the lab from the previous week, you kind of get 2 weeks to do that. So it's kind of like that lab is kind of distributed over those 2 weeks to give you flexibility again there with fall break scheduling. And then we've got then that Thursday after fall break, that's when your stage 2 would be. Both of those stages you can take from remote, regardless of which option. I will be in the class, regardless of which option, for those class periods in case you want to do them in the classroom here. Where in stage 2, you can work together in groups, just maintaining safe distancing and all of that. Whereas stage 1 would basically be just proctoring in the lab or in the classroom here. So those are your 2 options, either all the same week, Tuesday, Thursday, or separated by fall break, Tuesday, Thursday. So are there any questions about those 2 options? Pretty clear. And there's a survey on, and I basically made the survey a lecture credit. and I added another lecture drop. So those of you who complete the survey, regardless of which option you picked, you'll get to drop 6 lecture attendances instead of 5. And if you don't complete it, then the survey gets dropped and you still got your 5. So any questions about that? Pretty clear. And I've left that open until, I think I make it due Friday night, open until early Saturday morning. So this week sometime, just go, it's just one question, tell me which option you'd prefer, and I'll use that to decide whether to move stage 2 before fall break or leave it after fall break. All right, any questions online? Check both. Meeting pulse, okay. Great. All right, so before I go into the main stuff here, let's do a quick post-mortem on lab 3. So pull up lab 3. Right here. All right, so lab 3, this is an introduction to using Monte Carlo methods, primarily using Excel. So I mentioned that Monte Carlo methods are a way of using simulation to solve numerical problems. And so these are problems that you probably, in theory, could write out mathematically and solve them that way, but it might be intractable. So you might be able to write out the form of an integral, but you can't actually write out the solution of that integral because it's just, and there are certain mathematical problems where it's possible to write the problem, but it's not possible to write the answer. And so you could say, well, how do I approximate the answer? Well, there are numerical methods that allow you to approximate the answer, and some of them are based on random sampling with the computer. In other words, simulation. So the first kind of the standard problem in this is like estimating pi. So there are a bunch of ways to estimate pi geometrically, maybe using Taylor series expansions and all sorts of things you might learn in math class. Or we can kind of take a sampling approach. We can say, well, if we have this question we'd like to answer with an experiment, what fraction of uniformly distributed random points fall inside a circle? So this is like if I manage to throw a dart at a dartboard and the X and Y coordinates end up being uniform distribution. So there's an equal density that I could hit anywhere along the X or anywhere along the Y. So I can point with the pointer here. The uniform distribution, I could hit anywhere along the X or anywhere along the Y. Then you can ask, well, what's the probability that I'll actually land a dart in the circle? And as long as it's a uniform distribution across X and Y, then the probability that you land inside the circle is just the ratio of the two areas, the area of the circle divided by the area of the square. Well, we know the area of a circle is pi r squared. We know the area of this square is 2r squared. And so when we expand those things out, do some cancellations, then you find that the probability of landing inside the circle is pi over 4. So we can just, for numerical convenience, simplify and just focus on the upper corner. And we get the same sort of trick here where if the area on the top here becomes pi r squared divided by 4, and the area on the bottom just becomes r squared, and you end up getting the same result out, pi over 4. And so that's what I've got here. So we just zoomed in on that corner. And so if I was throwing darts at this shape, this square, what's the probability of getting things inside this arc? It's going to be pi over 4. It's just throwing uniformly there. So just dropping darts on this thing. So then the thought would be that, well, if I just do that experiment, so if I throw a bunch of darts at this dartboard, then every time I throw those, I'm going to get sort of a win or a loss. And the ratio of wins, landing inside the circle, that divided by the total is going to be an approximation of this probability. In other words, it's going to be an approximation of pi over 4. Another way to look at it is every time you throw a dart at this thing, you're effectively trying to estimate pi, but you only get an option to give 2 answers. If it lands inside the circle, you get an answer of 4. If it lands outside the circle, you get an answer of 0. So at every one dart, you'd say, what's this one dart's crude approximation of pi? This dart's approximation is 4. This dart's approximation is 0, and so on. And if I average across darts, then I'm going to get slightly, well, quite a few more darts answering 4 than the ones answering 0. And if I average across my population of darts, then the average belief from those darts is that pi is 3.14159, et cetera, et cetera. So that's what we're doing here in Excel, is that we generate rows, or each row is a throw of a dart. The x coordinate comes from 0 to 1, the y coordinate comes from 0 to 1, and then we can just ask, is the xy coordinate inside the circle? And let me enable transcript. I know that I usually do that. I just realized that I did not. So apologize for those online. If I can find it. There it is. All right, so I can then count. So I'm going to get some columns that are true, a 1. Sorry, some rows that are true, a 1. Some rows that are 0, a false. And if I take the average of that, I will end up getting an approximation of pi over 4, which I can multiply by 4 to give me a approximation of pi. So that's what I'm doing here, is I'm counting the number of rows that represent darts inside the green space, divided by the total number of darts, and then multiplying that by 4, and that gives me an approximation of pi. That is a random way to estimate pi. Does this make sense? This weird little setup here where we just throw random numbers and we use the geometry of where they land to end up backing out interesting quantities, in which case we know here that the geometry involves a pi. And so that's the trick we used here, is that we know the physics of the world, pi is embedded in that world. And so if we randomly experiment with the world in the right way, the world will give us pi back. And that's what we're doing here. Does that make sense, what you guys did there? I know the first time I ever did this as a student, and maybe I just, as a nerd alert, is that I thought this was pretty cool. Like the first time I just threw random numbers into a spreadsheet and got pi out. At that point in my, academic career, the only way I'd ever approximated pi was with things like Taylor series expansions and things like that. And so the fact that I didn't even need a whole lot of math, I just could just draw, as long as I drew enough rows. And if I wanted more and more precision, I just drew more and more rows. I didn't have to take extra derivatives or anything like that. It was, it seemed really elegant to me. So it was very formative in my career the first time I did this sort of thing. So it's exciting to do that here. Now, each one of you is going to get a different estimation of this pi over 4, or of pi. Some of you got 3.15, some of you got 3.13. I could ask each one of you what you got. And I think, in fact, we have to usually explicitly tell people that it's okay that the Excel spreadsheet they submit doesn't have the same number as they submitted on their Word doc, because every time you open Excel, it draws a new set of random numbers. And so people will say, oh, my Word doc said 3.16, but then I reopened my Excel and it said 3.12. And I didn't cheat, I swear, I didn't copy my neighbor. It's just Excel didn't have the same number. And we understand that because Excel doesn't draw the same random numbers every time you open it. So even yourself, every time you open that spreadsheet, you're going to get a different approximation of pi. So what we can do is we can look at these numbers, these zeros or ones or zeros or fours, depending on how you look at it, and we can calculate the mean. So for 500 rows, you can imagine my mean was 305. And then you can define the standard error of the mean, which is just effectively the standard deviation of those zeros and ones, or zeros and fours in this case, divided by the square root of the number of samples. And we'll talk about where that comes from. But what the standard error of the mean is, and hopefully you've seen the standard error before, which is different than the standard deviation, is it is the standard deviation of an estimator of a mean. So we estimated the mean of this population to be, around, in this case, 3.04. But that estimator, every time I redraw those 500 rows, I get a different number. And so we not only have to estimate the mean, but we also have to estimate the standard deviation of the estimator. So what this is sort of telling us is there's going to be a spread. If every time you open the spreadsheet, if you have 500 rows, sometimes you'll get low numbers and sometimes you'll get high numbers. And so this is trying to capture that spread. And the more rows you add, then you're getting less spread every time you open that spreadsheet. Now, we can make this a more useful quantity by converting the standard error of the mean, and this is something we're going to learn how to do after the midterm, into a 95% confidence interval. And so a 95% confidence interval is just an interval for which, if you draw 100 confidence intervals, 95 of them will include the true population mean of 3.14. So we can see that for 500 samples, the confidence intervals are really long. And that makes sense because we can get estimates that are really long. But if we include the confidence interval, this interval estimate, then we're sort of sure that somewhere in this giant interval will be the real mean. So when you hear a confidence interval, you shouldn't actually think about the numbers inside the interval. You should be thinking about the numbers outside the interval. A confidence interval communicates the numbers that the thing you're trying to estimate definitely is not. So if somebody says, we estimated pi to be somewhere between 2.9 and 3.19, then what that tells you is not what pi is, but it tells you that pi can't be really any lower than 2.9, and it can't be any higher than 3.19, but it's somewhere in between. That's what you should take from a confidence interval. Now, if we add more and more rows, those confidence intervals shrink, but notice that every confidence interval always includes 3.14. So if I didn't know pi ahead of time, then I wouldn't know what the true population mean was. But every experiment I'd ran, I would be pretty confident that with 95% probability that the interval, the confidence interval that I got out, regardless of how many rows I put in my experiment, was going to include the true population mean of pi. And that's what this is kind of showing here. So even though this is the reason why towards the end of the class, we're going to move you away from point estimates. So we want you to get to the point in your life where whenever someone asks you for an estimate of a parameter, you never just give them a mean. You either give them a mean and a standard error of the mean, or you give them a confidence interval, because you can never be confident about a mean. So every time you open that spreadsheet, you got a different estimate of pi. And so what is that supposed to say? What is pi based on your spreadsheet? Well, if you throw in the confidence interval, it communicates so much more, because you're not actually saying pi is 3.2. What you're really saying is pi is not 2.85, is not 3.25. And if you want me to tighten this up, then you're going to need to give me more money so I can run a bigger experiment so that I can get more data, so that I can squeeze this confidence interval down. So that's really what you're doing when you're taking more samples, is you're squeezing confidence intervals down. So we're going to start the class thinking in terms of means, so-called point estimates. We're going to end the class where hopefully you will not ever feel the urge to give a mean, so that in your final project presentations, when you're estimating things from your sims, you'll give me intervals, because intervals are the only thing we can be confident about. And we quantify how confident we are. 95% confidence interval. If it was a 100% confidence interval, it would be the whole real line. If it was a 2% confidence interval, it would be very, very narrow. But it would mean, so the more and more confident you get, then that just means the more and more high probability that you actually capture the mean. So larger confidence intervals, larger confidence means coarser intervals, lower confidence means finer intervals. So there are questions about that. Just trying to provide perspective for why every single time you ran your 500 rows, you got a different value of pi. How could you possibly make use of that? Well, we'll make use of it by using interval estimates, not point estimates in the end, when we start really analyzing these things. Is that clear? Are there questions about that? Just providing a roadmap for where we're going as we start trickling in more statistics. Looking online to see if there's any questions. Okay. All right, so practical lessons for this point on, if you're doing sims in Excel, RAND generates a number uniformly distributed between 0 and 1. We'll talk more about what that actually means as we start getting into probability and such. But then so that was a practical lesson for this one. Okay. So in the second part of that lab, we had that stochastic activity network, kind of the simulating a breakfast part. And we had a 3-part activity, a 2-part, and a 1-part activity. And when you look at these, you say the average duration of each branch is the same. This is an average duration of 9. This is an average duration of 4, 5 plus 4, 5. So that's an average duration of 9. This is an average duration of 3, 3, 3, and 3. That's an average duration of 9. We all know, due to linearity of expectations, all 3 of these, this top one, and part 1, 2, and 3, all of these have the same average per path. So it seems like the whole network should have an average duration of 9. So what we do to test that is we generate a spreadsheet kind of like this one, where we can generate a 3-part duration. So the top path, a 2-part duration, the middle path, and a 1-part duration, the bottom path. And so this is a sum of 3 random variables. This is a sum of 2, and this is just 1 random variable. And we then take the max of these, and then we ask which path is equal to the max. And that tells us which path is the so-called critical path. And so we can then analyze this little spreadsheet. And what we find is maybe surprising, is that the duration, if you look at the distribution of all the durations over the whole network, you don't get an average of 9. In fact, most of the realizations of this network take much longer than 9 minutes, much longer than the average of each individual path. The average is actually, say in this case, 10.2. Now, of course, there's a confidence interval around that, but for mine, it was 10.2. And if I look at my critical path duration or distribution, again, there are confidence intervals around these, but for my run, I got not a 33, 33, 33, as you might expect. It's just sort of random chance which one is the longest path. I see that it is less likely for the top path to be the critical path than the middle path. And both of them are far less likely to be the critical path than the path that only has 1 step. So this is telling us that even though the averages match across the 3 paths, then I get a very different distribution of who takes longer. And somehow this thing combines to make the whole network take longer than the average of each individual network. And you say, well, how does that happen? And so this is just showing like a new additional sample. So I'll go from 500 to 1,000, things get a little more refined, but I get roughly the same distribution. I can now go to 10,000 rows, things get more refined, but again, same average, 10.2, basically the same critical path duration. And the trick here is that if you were to take a histogram of the bottom path, it would be uniform from 6 to 12 as we expected. Now the middle path is the sum of 2 uniforms. Now the sum of 2 uniforms is not uniform. It's if you take more advanced classes in probability, you'll learn it's the convolution of 2 uniforms, which gives you a triangular distribution. Logically, the way you can think about this is you could say that if I truly had a uniform from 6 to 12 versus a uniform that was from 6 to 9 added to another uniform that was from 6 to 9, in order for me to get 6 minutes, then this one here, both of those activities would have to both take their minimal amount of time. In order for this middle branch to take its minimal amount of time, both of the independent activities in the middle branch would have to take their minimal amount of time. And it's really hard to do that because they're independent. Like there's no way to guarantee that the first activity, because it was minimal, that the second activity will also be minimal. So that's rare. That will rarely happen. Same thing on the other end. In order for us to get 12 minutes out of the middle branch, both of the middle 2 activities have to, even though they're independent, take the maximum amount of time. So one activity has to take the max, and then the other one also has to take the max, and that is very unlikely to happen. So the most likely thing that's going to happen is that they'll both take their average amount of time, and that's why we get this mode, a strong mode, right at the average for the path there. So summing things together, even though the mean stayed the same, causes the tails of the distribution to pull down. And we get an even stronger version of that up here when we have 3 of these things. Even though the means all add up to 9, it's very rare. In order for me to get 6 out of the top branch that has 3 activities, I have to have all 3 activities simultaneously happen to end up running their minimum amount. So minimum plus minimum plus minimum gives me this 6, and that is extremely rare. So it just keeps pulling those tails down. So what you're seeing here is the central limit theorem unrolling in front of your eyes. The central limit theorem says is that if I add up a bunch of independent random variables, then the sum of those independent random variables will tend to be distributed like a bell curve, like a normal distribution. And that's what you're seeing here. Add 1, add 2, add 3. If this keeps on going up, add to infinity, then this will look exactly like a normal distribution. All right, so, and because of that, this is the reason why the bottom branch tends to take the longest amount of time, because while it's very rare for either of the top 2 branches to get anywhere close to 12, whereas in the bottom branch, it's just as likely for it to take 12 as it is to take 6. So when I'm taking the max of all 3 of these, then regardless of what's going to be happening, regardless of what good luck I'm going to get here, then I might have bad luck here. And if I do happen to have good luck here, there's still a good chance that these are going to be greater than this. So there's the max operation kind of creates this sort of unfortunate situation where it's going to naturally push the mean higher. And then the fact that one of these branches has so much probability over here, then it's going to drag it even further higher, which is the reason why we get this massive shift from 9, where you might expect it, to 10.2, and while the critical path distributions look like this. So hopefully all of you got critical path distributions that looked kind of like this. It's fine if it is plus or minus a few percentage points. Again, it's an experiment. So every time you run it, you're going to get some noise, but the same qualitative shape should be there. And hopefully you got an average which was significantly larger than 9. So are there any questions about that result that came out of this lab 3, this stochastic activity network? Again, these are distributions that we might be able to work out mathematically, analytically, out on the board, on the whiteboard or back of an envelope. But it might actually be, even though it might be possible to write out the problem, it might be impossible to write out the solution, which is the reason why we use Monte Carlo, where if we do the Monte Carlo runs, we can run these experiments and then generate these distributions or these averages, and it gives us a numerical approximation to the analytical solution, which may be impossible for us to write out. And so that's the strength of Monte Carlo simulations. Let me see if there's questions online. So, I mean, the basic, and this basic idea came up when they were developing the nuclear bomb. They had to figure out, they had to solve actually a bunch of complicated double integrals, which they could not do. And they said, well, for the computing resources we have, what can we do? And they figured out that if they were clever about randomly throwing things, randomly drawing numbers, and then selecting numbers out, then they could actually solve very complicated numerical problems. And they had to come up with a code name for this method, which at this time was very top secret. And they came up with Monte Carlo, named after the casino, and the general idea of random chance. And so the idea of using random games to solve hard numerical problems. All right. So a practical lesson here is that if you want to generate a uniformly distributed random number between a lower bound and an upper bound, I gave you a formula for that. You take a uniformly distributed random number between 0 and 1, you scale it up by the range, so that's b minus a gives you the range. And then after it's scaled, so now it goes from 0 to the range, you then shift it over by the lower bound. And that gives you a uniformly distributed random number between a and b. And so, so that's just a general principle here, that we can take one type of randomness, a uniformly distributed random number between 0 and 1, and turn it into another type of randomness, a uniformly distributed variable between a and b. The same way when you're rolling a dice in a in a game, a board game, you have one type of randomness on the dice, but then the rules on the cards that tell you where to roll and what outcomes of the rolls turns that randomness into another type of randomness. And that's all we're doing here. So if, so I can generalize these ideas to say, well, what if I, again, this board game idea, if I have outcomes like 1, 2, and 3, and I want to realize them with certain probabilities, like in those inventory management examples that I showed from last time, how do we do this? And this is covered in the lab, though you didn't really do an experience or a part of the exercise with this. And the way we can capitalize on that is if we look at a uniformly distributed random number between 0 and 1, it has this interesting property that the probability that the uniformly distributed random number between 0 and 1 is less than any boundary, 0.2, is equal to that boundary. So the probability that this number is less than 0.2 is 0.2. Less than 0.7 is 0.7. And the probability that it's in a range is the length of that range. So the probability that this number is between 0.2 and 0.7 is 0.5 because it's 0.7 minus 0.2. So this here gives us a lot of power because it suggests that any probabilities we want here, we can, in theory, draw a random number and then ask, is it within ranges whose probabilities match up with the ranges that we want for these outcomes? And so I draw a single random number and I just check, is it between 0 and 0.2? If so, I'm going to give you an outcome 1. If it's between 0.2 and 0.7, I'll give you an outcome 2, and that'll be 50% of the time. If it's between 0.7 and 1, I'll give you outcome 3, and that's 30% of the time. So I can now simulate these discrete outcomes with desired probabilities just by drawing a single random number and then checking for which range it lands in. And so there is a generalization of this where if I calculate the cumulative distribution, and we'll refresh all our memories about what cumulative distributions are, but please remember from 380 or 385, I just summed up the probabilities. So they go all the way up to 1. So it's just 0.2 plus 0.5 is 0.7, 0.7 plus 0.3 is 1. And from here, I can use the cumulative probabilities as my boundaries. So for any discrete outcomes you want, if you write the cumulative distributions, you then get the boundaries for this like board game card, just a card that says if you roll a 0 to a 7, do this. If you roll an 8 or a 9, do this. If you roll a 10 through 16, do this. Those boundaries for that card just came out of the cumulative probability. So this is a recipe for any single discrete random variable that you want to draw in an Excel spreadsheet. You just calculate the cumulatives and then do a bunch of if-then statements to see where you land. And so that's what I can kind of show here is that I can draw a single random number. And the key here is it's a single random number. It's not, this if statement has to refer to a single random number, not independent random numbers in here. But by drawing that single random number and then picking if statements, then the outcomes will be the discrete outcomes 1, 2, and 3 that will be according to these probabilities. So it is a way for us to simulate any discrete random variable. So that's really cool. And we'll find that we can generalize that for continuous random numbers as well. And I won't go through that here, but this is what's coming up here. As you'll see in homework D2, you'll check an opportunity to practice this. And then we'll talk about when we get to that in lecture D2. So we can do this same process even for continuous random numbers. So I thought I had actually a little diagram of that, but I guess not. So any questions about any of that? That's all I've got is my post lab 3. Those are the kind of things I wanted you to see coming out of lab 3. The big part of lab 3 was just getting familiar with the idea of Monte Carlo sampling and the idea that we can draw random numbers in Excel, transform them in unique ways in order to solve other problems like calculating pi or try to describe a stochastic activity network. And that's the last that we're going to do with Excel. Was that a question? Okay. Questions online? All right. Well, I hope that lab was, I hope these labs feel like they're getting progressively more useful and less tedious. But we shall see, I guess. All right. So let's hop back. So now we're going out of Excel and instead, good, all right. All right, so we talked about discrete event system simulations you could do in Excel. There was a recent article in ORMS Today, which is like a journal for operations research, management science, on simulated worlds, that was sort of surveyed a bunch of different ways in which a discrete event system simulation has become really useful for a wide range of divergent fields, from manufacturing to healthcare to other service systems, logistics, et cetera. And it's just kind of a nice survey there, where they link to a bunch of different simulation packages, including things like FlexSim, other packages that I've mentioned, although our big focus has been Arena. So I posted that on Canvas. If you're interested, I recommend taking a look through there. It just kind of gives you a nice kind of top level survey from somebody working in the industry about the value of simulation and all these different frameworks. Now, what about other frameworks other than DES? And so I mentioned earlier in the class that simulation, I kind of grouped into three main groups: agent-based modeling that has a lot of realistic detail and scaling. The matrix resurrection is coming out soon. Back in 1999 when the Matrix came out, that was an influential movie of my youth, and it's effectively about a giant agent-based model that is running the world behind the scenes. There's also a nice movie called 13th Floor, came out also in 1999, which is really a good movie, but it came out at the same time as The Matrix. I don't think anybody saw it, but it was even more like very much like, what if we are agents in a giant agent-based model? So that's kind of on one spectrum. So very realistic detail and scaling, whereas on the other end, we have like system dynamics modeling, which I'll re-summarize here, which is more metaphorical. So it's very generalizable across a wide range of systems, but it often lacks all of the peculiarities of a particular system. And so if I start with like system dynamics modeling, just as a reminder, so the way system dynamics modeling works is, instead of thinking about the entities and resources that we do in discrete event system simulation, we think about stocks and flows. So our worldview in system dynamics modeling is that time is flowing continuously, and it's constantly, stocks are trading amongst themselves, and the changes in stocks are represented by flows. And so it's like water moving around a series of pipes. And so this diagram that is used to draw inside system dynamics modeling tools is a graphical way of depicting this differential equation down here. So you draw graphically a bunch of these fluid dynamical processes and how they link together. And what the computer system does behind the scenes is generate a bunch of these equations and then numerically solves these equations, so that you then get to see the output. Like it's like, writing around a differential equation, and then you would normally integrate it and then maybe plot the result. Well, this is just jumping straight to the plotting, so you don't actually get to see the symbolic result. That's how these system dynamics modeling tools work. And so, like a sort of a famous example here that's very relevant, I guess, to these days is the SIR model, which is a disease model, where you think of the world as three boxes: is a group of susceptible people, a group of infectious people, and a group of recovered people. And continuously over time, you get trading between these boxes. And so there are flows that are going out of the susceptibles and in to the infected bucket, and then out of the infected bucket and then in to the recovered bucket. And so we can write the right-hand side here, capture these equations that get labeled on the flows, and we then can put that into a graphical model like this. So this is the way you'd write it mathematically. This is the way you'd code it up. So you have the susceptibles, the infectious, and the recovereds. You've got flows showing who trades with who, and then you've got these little lines showing what things depend upon other things. And so the rate of conversion from susceptibles to infectious depends on the contact rate. And that contact rate is effectively a parameter. And so if you can convince people who are infected not to be running around the world, then it reduces this contact rate. So it reduces the flow from susceptible to infectious. If you can't, then that stays high, and then this becomes much faster. So it's a way of a coarse-grained view of the world where everything is kind of a flow that you're constantly either impeding or allowing. And that's the way system dynamics modeling works. And so this is something that is covered in 477 and a number of other classes. In sustainability, it's covered. In business, it's covered. It's a very popular modeling framework, but it doesn't quite have the fine-grained details that we would need to optimize, say, a manufacturing system. Now, what we're going to give you a direct introduction to this week in lab is agent-based modeling, where, like the matrix, like the 13th floor, you focus on interacting individuals that each have their own agency. And so this idea here is I could have like this is inside NetLogo. I've got a bunch of wolves and sheep, and they actually move around a simulated world, and that world has grass. And so the sheep can only survive if they can find grass. And so these sheep have to actually move to patches with grass. When they eat the grass disappears, the grass regrows at a particular rate. The wolves can only survive if they can find sheep. And so there's a three-way interaction between the grass, the wolves, and the sheep. And we watch this in 3 space unroll. And then we can watch the kind of outputs of these populations here, and we can change parameters like how quickly does the wolf reproduce? How quickly does the grass reproduce? And we can see how these things change the qualitative nature of these curves. So we actually generate kind of like a real world, and we just see what happens. And so we don't have a lot of math behind the scenes. It's mainly trying to generate realistic interactions and then just see what happens and describe them as we would when we're experimenting with the real world. And so we often see individual-based modeling or agent-based modeling, same term, in biology to study things like fish schools, bird flocks, and complex ecosystem interactions. And so there are farmers who might have certain land use management policies, which causes an influx of locusts, which changes different dynamics of other things. So farmers affect where their goats are. Their goats defecate in different places. That defecation changes the nutrient content of the soil. That changes whether you get locusts or not, and so on and so forth. And all that could be wrapped up inside an agent-based model that would be very difficult to write out mathematically, but very easy to write out at those small system sort of scales there. Social scientists use agent-based models to study ancient civilizations, modern societies, organizations, stock markets. Even participatory simulations. And so the matrix, that my example there, that is sort of an example of a so-called participatory simulation where you've got non-player characters that are totally in the game, but you also have humans that are hooked up to monitors who control their agents. So the agency is controlled by logic for the non-players. It's controlled by the humans for others. And so in agent-based modeling in social science, you often see people that are actually hooked up into these like giant virtual worlds where they're participating with each other and with these other characters. And sometimes they don't know who's real and who's not. And they use that to study hypothetical situations. What if we put people in these particular situations that we maybe couldn't put people in the real world? You're going to study it that way. And then engineers use ABM and multi-agent systems, a related framework, to study things like if we are studying swarm robotics, we got 1,000 robots that can move around anywhere on a factory floor, assembling things. What are the right strategies for such an unstructured environment? Well, that doesn't really fit well with maybe discrete event system simulation, but we can simulate that and we can see how many parts are produced per hour out of our multi-agent system by just simulating these robots moving around a virtual factory floor. So these are things that we can do with agent-based models. A lot of different frameworks out there will get introduced in NetLogo and Lab 4. There are Python-based frameworks. AnyLogic, which is a framework used in 477, also has agent-based modeling behind the scenes, and lots more. So there's a lot of support out there. We use NetLogo because it's kind of the simplest one to kind of get started with, but there are far more sophisticated frameworks out there as well. All right, so the basic difference between agent-based modeling and our discrete event system simulation is the entities are referred to as agents, and we call them agents because they have agency. They don't get pushed around by external processes. You have to model the logic on each individual agent. So because we don't have external processes that govern this whole thing, then time cannot evolve with the event scheduling worldview. We don't kind of know what the next event to schedule is. So instead, what we usually do is we make a guess at what's the smallest unit of time for which we don't think agents will make any major decisions. They won't change their behavior too much. And so we might think that's a second, or there might be 100th of a second or 1,000th of a second. And then we jump ahead by second by second by second, and then implement our agent-based logic. So we go around every 10th of a second, we'll ask every agent, based on the state of the world right now, what would you like to do? And agent A says, I'd like to move left. Agent B says, I'd like to move right. Agent C says, I'd like to stay here, and so on. And then we then implement that in the next 10th of a second, and that changes the state of the world. And then we ask them again, at this state of the world, what would each one of you like to do? And we allow each one of them to do that. And that's how an agent-based model moves along. So every tick of the clock is one of these minuscule periods of time. And so we try to make those as small as possible so we don't miss anything during our simulation. So that's kind of all kind of summarizing here. So when do you use, and so I'll give a kind of jump to more concrete examples here in a second. There's a really nice article that I've posted online called The Pedagogy of Zombies. And this was in operations, again, ORMS today in October 2015. And this was a company that was bringing in industrial engineering interns and was actually upset that, and they did a lot of contracting for NASA. And they use agent-based modeling to study how commercial airlines respond to policy scenarios and generally a bunch of different airline-related scenarios. And they used agent-based modeling for that. They'd bring in their IE students, and their IE students didn't have any background in ABM. And so they then compensated for that by creating a competition that they sponsored that was then co-sponsored by IISE. At that time, I think it was just IIE. And in that competition, they would basically give them a task of building the logic for humans in a world infested by zombies. And you didn't know the floor layout maybe ahead of time, but you had to come up with a good strategy for a human for a generic floor plan to escape these zombies. And then at the time of the competition, you could then give this floor plan out and you pepper your humans that have your logic around, and they then go off and do things that have your logic. They try to find rooms with particular shapes. Maybe they try to cluster together. Maybe they try to separate out or whatever. And then the zombies, which are implemented by the company, the LMI, they then go through, and after this runs for a certain amount of time, you see how many humans were left over. And so you can then compare the solutions based on how well they survived. And so this is kind of a cute sort of tongue-in-cheek, it doesn't map to any particular OR type problem, but it's a great way to motivate this idea of just of programming the logic for each of these individual humans and then competing them against each other. And then the funny thing is, I think last summer or so, I ran into a grad student at UNLV who was actually interested in these scenarios where you might have somebody coming into a school, for example, maybe with a weapon and things like that. And he wanted to figure out, how do we build buildings that provide as much shelter as possible? And he did exactly this, not knowing about this, where he built a model of how he thought humans would behave inside buildings. And he would then have you know, these individuals coming in that we could sort of say, without trying to trigger anybody here, we could just pretend like there were zombies there, and he would compete different building floor plans against each other to see which floor plans were more successful at keeping the most amount of people safe. And so it was, you know, a nearly identical scenario here, even though they weren't directly related to each other. And he did that all inside an agent-based modeling tool. So those are the types of things that you can do with ABM. Southwest Airlines uses ABM all the time. They've done for their cargo management, for their boarding policies. I talked about this example with disease spread on planes, and so on. So that's kind of the high level of ABM. And I want to spend the last little bit here just giving you an intro to NetLogo, so that you're prepared for Lab 4. But are there any questions about this general structure of, you know, we were now contrasting discrete event system simulation, which is the rest of the semester, with agent-based modeling and system dynamics modeling. Any high-level questions about these three frameworks? I hope you can see there are certain systems that you could probably study with more than these frameworks. And under certain research questions, one framework maybe makes more sense than another. But sometimes you got to try one and before you realize that maybe the other one was better used. So sometimes I'll try an ABM out and then I'll realize that really things are more regular than I expected and it's much faster for me to simulate in a DES. And so I'll shift out of the ABM and I'll do it in a DES instead. So that's pretty common. All right, so let's see NetLogo here. I might just open up NetLogo, but let me make sure I hit the important points that a past version of me thought I should hit first. And NetLogo's up, okay. All right, so NetLogo is a Java-based, so works on all platforms, agent-based modeling tool developed with NSF funds at the University of Michigan State. It's in the University of Michigan or Michigan State. Well, I guess it was developed at Northwestern, then Yuri moved. So it was developed at Northwestern by NSF, so it's totally free. It's still under active development. It's a very popular tool. It runs on Windows, Linux, Mac, no trouble. Allows you to interact with your agents, modify control parameters, display variables. It looks a little old school when you see it, but it really is a very powerful platform. So, and what's neat about it, as of 2015, there's even a web version. And so you can actually go to this website and run NetLogo inside a web browser without actually having to download NetLogo. And you can even modify code that you see in there. You can't save anything out. You can't access data files or save out data files or anything like that. So it's a little bit limited, but what's really cool about this is I mentioned your stakeholders sometimes constrain what simulation packages you use. I've worked with stakeholders where we've needed to use agent-based models. And if I build the agent-based models in NetLogo, I can then give them a URL where they can run our model inside their web browser without installing anything and experiment with it. So I have to make sure the model is like easy to use, but they at least get a much better way of understanding what I've generated if they've had a chance to interact with it itself. And so even though NetLogo may not be the most glamorous agent-based modeling tool, things like this allow you to easily share and disseminate your results and open up those communication pathways with your stakeholders that maybe some other tools it's harder to do because you got to get them to download some tool and install it and know how to run it and all those sorts of things. And this even works on mobile devices. So I can sit at a conference with a tablet up and actually be running an agent-based model live in front of somebody who's walking by my poster at a conference. So what sort of things can you build in it? These are examples. This is from a postdoc who was down the hall from me at the time. This was a project that was funded by NOAA, National Oceanic and Atmospheric Administration, where they were interested in how you get people from evacuating from areas like Florida when there's a hurricane coming by, when you have control of different types of media or opportunities to use different types of media. So they simulated a a huge number of agents, people who live in Florida, each one of them that can respond to things like social media, radio, TV. And this tool allowed them to simulate what happens when you start sending out evacuation notices very early or late. So if you send them out too early, then there's psychological logic in these agents that will cause them to kind of stop paying too much attention to every notice that comes out that isn't followed by an actual immediate danger. So this allows them to realize that, well, maybe certain platforms like social media, we send out notices early, and other platforms, like TV, we send out load notices late, and that's the best way to maximize actually getting people to evacuate out of Florida, or some other policy. So this is the way they could experiment with the portfolio of media platforms that they had available for sending out evacuation. So when this sim would run, you'd actually see this simulated hurricane come across here, and you'd watch the agents move all around Florida here. And so under different media policies, you would see different response rates from people moving out of Florida. So that's an example of something that you can do inside of NetLogo. So, and this is actual, I think, GIS data that they loaded in on Florida. So they may not have highways and everything drawn in here, but I think the agents are moving around actual transportation networks inside Florida. You can do things that look a little bit more cartoony. So this is a stock example inside NetLogo. So I probably could open this up. I'm just afraid that at the default resolution for this projector, that it's not going to look great, but let me see if I can open it up. Biology, let's see this one. So this stock example here is an example where there's an ant nest here and 3 different feeders that have different amounts of food in them. And these ants don't know where the feeders are, but they have the ability to lay pheromones on the ground. And without the pheromones, they move randomly. But with the pheromones, they're attracted to the pheromones. And so these ants have policies in them that if they find food, they will lay a trail from that food back to the nest. And so we might wonder, what do the dynamics of such a system look like? Well, we can simulate that in NetLogo. And what you end up seeing is there's an initial exploration, and then you can kind of watch these kind of exploration exploitation dynamics where they'll end up focusing their effort in kind of a priority situation here, where they end up eating one thing and then another, and then finally finding the other one. And this one's so far away that it's sort of difficult for it to establish one of these trails. But we can go in and say, well, how if ants did work this way, how would things like evaporation rate affect these dynamics? Well, I can change the evaporation rate to be very low, for example. And when I run that, then these trails stick around a lot longer, and I might get very different exploitation dynamics. If I change the evaporation rate the other way, so if I were to go like this way and rerun this simulation, then we can see that they can't ever establish a trail because it evaporates too quickly. So even though this is kind of a cartoony, kind of looks a little silly model, it helps us better understand the potential role of evaporation rate. So if we took ants that were in the tropical rainforest and we then put them in the desert where things evaporate a lot more quickly, it might completely mess up their foraging, even if they had enough food available, because their communication mechanism kind of depends upon there being these chemicals that have a latent sort of effect on the world around them. So this is something that we can play with inside an agent-based model. Other questions about these examples here? Is it pretty clear kind of what's going on here? I'll show you the kind of internals in NetLogo here in a second. And so you're going to be playing with similar examples for the lab 4, one in kind of a forestry case, the other one is sort of like a marketing example, or it's actually a social science example. We get to play with a couple of different parameters, see how things work, and run some experiments to better understand how these complex systems work. All right, so All right, so what do we see when we open NetLogo? On this main page here, you have a bunch of input elements that you can pepper onto this, that you can choose the place. So there's sliders, input where you can type in numbers, there's buttons, and a bunch of other things here, plots down here, and then the actual world view where you're kind of got a top view here. There's also a NetLogo 3D where you can implement agents that move in 3 dimensions. And so that's also embedded within the program. We don't use that in the lab, but that is something that is available. And then you can, so like up, if you right click on this world, you can go into its preferences and you can change things like the size of the world. So you can say, the default size might go from -30 to 30, and you can change that. Whether the world wraps around on itself. And so the default world is a donut, it's a toroid. And so as you go off one edge, you pop in the other. As you go off the other edge, you pop in the other, just like you lived if you were living on a donut world. But you can actually make these hard walls as well. So there's things like that you can change. And then NetLogo's got this thing called behavior space, which you will work with directly in Lab 4. So under the tools menu, go to behavior space. And what's cool about this is it can automate running experiments. And so all of those parameters that were on that front page here, so like I've got diffusion rate, evaporation rate, et cetera, all of those parameters, you can then go up here and create experimental designs where it can say, I'd like to see all the failure rates from 0.05 to 1 in 0.05 steps, all of them crossed against this preferential attachment variable. I want to see that in both true and false. And so there might be, from 0.05 to 1, 20 or 21 different levels of that variable failure rate. And then there's 2 levels of preferential attachment. Well, it will then combine for every one of those. It will then do the full factorial design where it'll combine it with every one of these. So that's whatever, 21 times 2, that's 42 different experimental conditions. And then I want to say for each one of those, run them 10 times. And so then it'll then automatically move the sliders around, run each one of them 10 times, give you a result that's saved out to a CSV file, and then go through and run the next one. So it automates all of that for you. And then it even can distribute that across multiple cores on a multi-core system. So you can run all these things in parallel and get your sims done very fast. So that's behavior space, which you'll get a chance to use there. It automates the running of experiments, which is really cool. So in NetLogo, the entities are called turtles for historical reasons. There are different breeds of turtles. So you can say, generically, I have turtles, but I can create an ant breed, I could create a nest breed, I could create a food breed, and each one of these different breeds of entity or agent can have different logic. There are patches, which are agents that are not movable, but they're like agents that the agents can walk on top of. So if it's like this, there are these little carpet squares, the agents can move anywhere within the carpet square, then they also can move from carpet square to carpet square. So you have the opportunity to simplify your program logic to just say, what's the amount of food in this carpet square? What's the amount of food in this carpet square? And I can kind of keep track of that by asking the carpet square agents to update their amounts of food, and it like distributes my memory around these carpet squares. So it just makes programming easier by actually making these immobile agents that all the other agents walk on top of, and these are called patches. And then you can create links. And so you can say that 2 different agents, after they bump into each other, become linked. And you can then ask them, it's as if they create a network connection. And so from that point on, you can actually ask these 2 agents, even if they're separated by a long space, to maybe be coupled in some particular way. So you can say, well, they're gonna, whatever reward one agent gets, the other one also gets that. And then you can break those links. So these are the 3 kind of entities that you can use when you're creating models for whatever purpose. You don't have to use them all, but these are some of the degrees of freedom that you have. Within those, each patch has certain attributes automatically attached to it. Its X coordinate, its Y coordinate, its color. You can associate a label with it and a label's color. But then just like in Arena or really any other sim package, you can add your own attribute. amount of chemical deposited here, whether this has been walked on by an agent, etc. So you can add a bunch of different attributes to each one of these patches. For every turtle, it's got a bunch of attributes already associated with it. Every turtle's got a unique ID. Every turtle's got a breed. It's got a number of these other things here, but then you can add your own. So how long the turtle has been living, that could be one attribute. Whether the turtle has experienced a particular event before, and so on and so forth. And so you can add a bunch of your own attributes and change your logic based on those attributes. NetLogo is really great in that it comes with a bunch of pre-built models. And so if you go in the file menu on NetLogo, which is what I did with these ants, there is a models library. So it's probably hard to see because of the resolution for this screen here, but without being able to read all of this, what I'm trying to drive home here is there's a huge number of pre-built models that are in fields like art, biology, computer science, mathematics, networks. There's a bunch of these different ones that you drill down into, and you can either use these for what they are, or you can build on them to then modify for a system that you say, well, I'm not interested in ants, but I want to build robots to do something similar to this. So I'm going to start with the ants model, and then I'm going to change it up to make it more appropriate for robots, for example. So this models library has a bunch of these pre-built models. They've got a bunch of things you can use in classrooms, and then they've got a bunch of coding examples. So you're like, well, how do I get something to bounce off a wall? Well, rather than trying to find it in one of these models, they have just bounce off a wall code examples, like real small bits of code already pre-built for you that you can use. So there's a lot of great resources already come pre-bundled with NetLogo. And I'm just kind of showing off some of these different models that come pre-built with it here. All right. And then inside every model in NetLogo, if you click on the info tab, if that person who wrote it did it well, then there's documentation that's built in. So, and this goes with the web interface as well. And so you don't know how to use the ants, you go over to the info and it'll tell you how to use it. And then there's a code tab. And so every model has its code exposed. And so you can go to the code tab and you end up getting code that looks like this. And so you have access to all of the NetLogo code right across the tab here. You can go back and forth between the interface and the code tab. And so how do these things connect together? If you go into these buttons, like there's a go button usually for every NetLogo model, and inside this go button, every time that button is clicked, it runs a routine in the code called go. So it's called whatever you type in here. So in this case, it's called go. And if I check this forever, then when you click the go button, it stays held down. And so every tick of the simulation, every 10th of a second or whatever your time step is, it then runs go and then runs it again and runs it again until you click on it again to pop that button up. So this forever checkbox here is what allows this system to run forever. Otherwise, if I unchecked that forever checkbox, I would have to click go manually in order to move the system from step to step to step. And that's how the time steps are working inside NetLogo. Routines for NetLogo look like this one. So this is, it's a little bit, it's the logo programming language is a little bit different than maybe what you've seen before. Instead of saying like function, it says to. So to go, this is the routine that is executed whenever you hit go. And because it's an agent-based model, the way you get things to work is a little bit funny. Like you might say, if I was in MATLAB or whatever, I'd say for I equals 1 to number of turtles. And then I might ask each turtle individually to execute its code. Here, all that's hidden behind this so-called ask command. So you say ask turtles, which basically says, I don't know how many turtles are out there, but all of the turtles are out there. I want them all to do this right now. And it internally is going to iterate through them in an order which shouldn't matter to you. And so this is an order that it will come up with. And so your logic can't depend upon this order. And then it asks each one of them to do what's in the brackets right here. And so it will run these things, and during your lab, you'll get a chance to look into what some of these different things do. And then once you've asked all the turtles to do things, then you can say, ask all the patches to do things. And so you can say, well, I want the turtles to move. But then once the turtles to move, then I want all the patches to update their chemical amounts. And that's what it's done here. So the ask command inside NetLogo basically iterates through agents of that type and asks them do whatever you're asking them to do. And so that's all I'm kind of saying here, is that you have to ask groups of agents to do things, and it'll iterate through that, and each agent will end up doing that. So that perspective is difficult to get used to. As you're looking at these different code, the commands might also be a little bit difficult to get used to, like what does ask mean? Well, under the help in NetLogo, they have a lot of really great resources, and one of them is like this. So if you go into this NetLogo dictionary or the user manual, both of these things will bring you to this page here that allows you to look at tutorials. It allows you to look at code samples, and then allows you to then drill down and actually say, well, what does these things mean? What does any question mark mean? Well, if you go to the NetLogo dictionary, just like in a real dictionary, you can then find what any is, and this is kind of the definition of any. And it says, well, if you said any question mark, whatever group comes after it, it will report true if that group is non-empty. Well, okay, that makes sense. So if any question mark, that just means is the thing that follows it, does it actually have any agents in it? So all of that is in that NetLogo dictionary. So if you're, and then it's got code samples as well. So here's a quick example of using breeds. And so if you look up breed, then it might have a code sample that says, well, for example, I could create a breed of mice, a breed of frog, and I can actually create plurals for that too. So I can refer to mice by mice or mouse. I can refer to frog by frog or frogs. I then can create mice attributes, mice own cheese, and then it's a little example code here that are related to those. So nice little code examples built right into the NetLogo user manual. So a lot of really cool stuff there. As I mentioned, there's code examples in the models library, which you can find, and so on and so forth. So just you'll get more experience with this working in lab, and just kind of just showing you a flavor of what the sort of stuff you're going to see inside the lab. So I want to close with this basic example. This is an entire NetLogo program where your turtles basically have a speed attribute, and all that's done up here is you create 10 turtles that have a random speed and a random heading or in a random position, each one of them. And then every time I hit that go button, I ask every one of them to go forward with their speed. And if they bump into any other turtles, turn around and basically change their speed to the minimum speed of all the other turtles. And then I move my clock forward. So that's an entire program that simulates a bunch of turtles moving around a world. And that's it, it's done. And so all of the timing and scheduling is done for you, and you can run that thing and see these turtles running around. I don't think I've got time to do it. So sometimes I would try to highlight this and paste it in, but I'm already running long today, so I'm not going to bother with it. But you're going to get lots of experience with that. So you're going to work with the Earth Science Fire model inside the lab. You're also, I think I've got you working with Hotelling's law, I've got you working with the Schelling segregation model from the models library. So you've got a social science model and a land resource management model that you're going to work with in the upcoming lab. So that's basically a very quick intro to NetLogo. You're going to have a more in-depth tutorial that you'll go through during the lab. But then that will be the last that we deal with agent-based modeling for the rest of the semester. We're going to be all DES from there. So any questions about that? Well, let me just put up the attendance exercise and 475 ATT. And the question that I have here for today is what is an example agent type or entity type in NetLogo? So I mentioned there's a couple of different, there's like a default type of agent in NetLogo is called a this. There's another type of agent in NetLogo is called a that. What's an example of the types of agents that you might see in NetLogo by default? So, so yeah, the default names for entities in NetLogo. And that's all I've got. I'll leave that up. If anybody's got any questions, I'm happy to stick around for a few minutes. Otherwise, we'll see you on Thursday. And don't forget about the survey due Friday. Let me know when you want that stage 2 exam.
Can I ask a question about the homework?
Sure.
So for the first question, I was curious if it's like actually a random number, because if you plug the parameters into the formula and then you do the modulus, like the modulus is like too big to have like a remainder, and it just becomes like what the formula is. So it's not really like random then, right?
Well, I guess the homework, I would follow the, I would say that that is, if I've done it right, I've chosen numbers that things won't be trivial necessarily, but of course, you know, anything that is not a random, I mean, computers can't generate truly random numbers, and so there's always going to be a formula involved behind the scenes. And but if you're having that issue and you want to email me, I can double check. I can see if there's any red flags in what you're doing. And I can also double check if there's any red flags in the numbers that I've given you, because I don't think I designed that problem so that it would degenerate into like 0, 0, 0, 0 or something like that. So if they are, either I
Like
did something wrong. Okay, go ahead.
it would just be like a linear pattern, just like increasing by like a number each time.
Well, again, I would double check your work, because and if you're still not seeing it, feel free to send me an email and I'm happy to take a look at it. But but it shouldn't have been designed so that it was like an obvious pattern coming out of it.
Okay.
So so that's kind of my hint that I would give there.
Okay, sounds good.
All right. I am going to go ahead and end the recording.
Professor, I had one more question.
Okay.
For the midterm, it doesn't say on the syllabus what time the test is.
Well, I sort of explained that because this semester is a little bit weird. I kind of explained that in the first lecture, is that for stage 1, you get like 90 minutes anytime you want that day. And for stage 2, you pretty much, it's untimed, you get all that day. So it can be taken completely remotely. If you want to come to class for either of those stages, you can. But because we've got some students that are stuck outside the country and so on, then it's more, the stage 1 is timed, but when you start it, it just has to be any time that day. And stage 2, you get all 24 hours to do it because it's collaborative.
And stage 2 can be done remotely too, right?
That's right. They both can be done remotely.
All right. Perfect. Thank you so much.
All right. All right. And then for anybody online, I'm going to end the things now. But if you've got any other questions, you can feel free to reach out to me. I'm just trying to get things out of the way here.